Let's go ahead and talk about our Born-Haber cycle. So for Module 13b, use the Born-Haber cycle to calculate your lattice energy or any other missing quantity and explain this process. Now again, I have this in here in this module because it fits in really nice with solid state chemistry. It is actually in the a different chapter in your textbook. It's under the Module 10 content in your textbook. So Lewis structures and all of that when we talk about lattice energy. So if you're looking for practice in your textbook, it is in the content covered in Module 10. So first, which of the following compounds will have the highest magnitude lattice energy value? When you're looking at lattice energy, what do you guys think? We talked about lattice energy previously. We know that lattice energy matters on the charge and the size of the molecules. So if I was to look here, I see KBr, K is a plus charge, Br is a minus charge. NABr, plus minus, LIBr, plus minus, RBBr, plus minus. They're all bonded to bromine. They're not all the same though. Even though they all have the same charge, they're all bonded to bromine, your cations are different sizes. So it's not E. We know, we talked about this in the Module 10 content, but we know that we have to look at charge, and we have to look at size. Larger charge is greater energy, smaller size. And we know that charge trumps size. They all have the same charge, so now we just have to look at size. KBr, NABr, LIBr, and RBBr. Well, RBBr is the biggest. KBr is next. NABr and lithium bromide is the smallest. So LIBr will be the winner here. This will have the highest magnitude lattice energy value. Again, lattice energy, how much energy does it take to actually break apart these particles? To break apart your lattice. Another way we can do this is what we call the Born-Haber cycle. And so the Born-Haber cycle looks at each individual piece that it takes to break up a molecule and uses Hess's law to determine some missing piece of the information. So I know this probably seems overwhelming to look at, but let's see. If we're trying to actually form sodium chloride, what's processes involved? We want to look at the formation reaction of sodium chloride. So the formation reaction, remember formation reaction by definition is the formation of 1 mole of your product in its most stable phase or stable state. That means I need 1 mole of sodium solid, because sodium solid is its most stable state, and I need a 1/2 mole of chlorine gas. Gas, because gas is the most stable state for chlorine, and a 1/2 mole because chlorine is a diatomic, and I just need 1 chlorine, so I need a 1/2 mole, or 1/2 of a Cl2. And I'm trying to find this process. Now I can look up the delta H formation, but what if I was instead trying to find the lattice energy or some other part? Let's think about the process for this to actually form. So I'm going to take sodium solid and a 1/2 mole of Cl2 gas, and I'm going to form NaCl solid. But what's actually happening here is first, I'm going to go through multiple steps. I have to form gaseous sodium from solid sodium. So I actually have to form sodium gas. That's sublimation. That's going from solid phase to a gas phase. So delta H, sublimation of sodium. Then I need to form chlorine atoms from the chlorine molecule. So I need to break up Cl2. Can't read that. I need to break up Cl2. Then I need to ionize sodium. I've got sodium gas, but I need sodium gas positively charged. All of that takes energy, hence the enthalpy increasing. I need to add an electron to a gaseous chlorine. So let's see, right here, this is your ionization energy. This is electron affinity. Adding an electron to the chlorine to form Cl-. Formation of crystalline solid from the gaseous ions, that's my lattice energy. This whole process is what's actually involved to be able to do this. So, looking at it mathematically, helpful hints. Both elements need to be transformed to gaseous ionized states. Cations, you're going to look up their ionization energy, because ionization energy is the amount of energy required to remove an electron from an atom in a gaseous state. For anions, you're going to look up the electron affinity, because electron affinity is the amount of energy either released or needed to give an electron to an atom in its gaseous phase. You might have to use multiple steps, such as vaporizing your bromine, sublimating your iodine, etc. They may not always be in the state you need, such as having to do sublimation on the sodium metal to get into the gas phase before we can go under the ionization energy. You may need to divide bond energy values. If you have diatomics, this happens, or polyatomics. By poly, I mean like S8, P4, that kind of thing. So let's say for sodium chloride, we're trying to find the lattice energy. We look up the enthalpy of sublimation for any solid. How much energy does it take to sublimate this? And this is all in your book, I promise. But looking up this energy, I get positive 108 kilojoules. Dissociation of Cl-Cl, half of your bond energy. Half of that bond energy is equal to positive 122 kilojoules. How much energy is involved in ionizing sodium? How much energy do I have to pay that sodium atom to take away one of its electrons in its gaseous phase? Ionization energy here, positive 496 kilojoules. Electron affinity of Cl, gas. How much energy does it take, or will chlorine pay me to give it an electron in the gaseous phase? Chlorine will pay me 349 kilojoules. And then the lattice energy of sodium chloride. How do I find it? Well, look up your delta H formation. You guys can figure this out. You guys know how to do this. If you're given the energies, you can figure this out. 411 kilojoules. Negative 411 kilojoules is the enthalpy of formation of sodium fluoride. Minus steps 1, 2, 3, and 4. Overall, you should find the lattice energy here, and I want you guys to calculate this on your own. You find the lattice energy here to be negative 788 kilojoules. We can do it this way, though, because of Hess's law. We can add up each individual sum to get over to our overall desired point. Use the Born-Haber cycle to determine the enthalpy of formation of lithium fluoride. So lithium fluoride, that's forming LiF. So you've got lithium solid plus a half mole of F2 in the gas phase. First thing you need to do is sublimate lithium. So lithium solid to lithium gas. 161 kilojoules per mole. Now that I've got lithium in the gas phase, I need to ionize it. So I'm going to look up its ionization energy. So lithium gas will give me lithium plus an electron. If I pay it 520 kilojoules per mole of energy. It wants to lose that electron, so the energy's not real high, but it's going to make you pay for it still. Step 3, dissociation of F2. Basically taking F2 gas and forming 2 moles of F gas. Breaking this apart. The bond energy here, 154 kilojoules per mole. So multiply this by 2. Or multiply this by 1/2, divide by 2. Overall, this will be, I'm going to write this under here, 77 kilojoules is 154 divided by 2. Formation of F minus, how much energy is required to add an electron to F. If I have F in the gas phase, I'm giving an electron. It wants it. How much is it willing to pay for it? It's willing to pay 328 kilojoules per mole. And the formation of LiF, solid from gaseous ions. Lattice energy here. -1047 kilojoules per mole. And again, we would have to provide these values for you, but when you're working problems on your own, you can look this up. The enthalpy of formation, delta H formation here, is equal to -617 kilojoules per mole. So these are all processes you've seen all semester long. We're just pulling them all together. And I'm going to let you work on this one on your own, but it's giving you a bunch of values, given the information below to determine the lattice energy of MgCl2. So you're looking at Mg solid plus Cl2 gas forming MgCl2. And find your delta H for your lattice energy. You should find it to be -2521 kilojoules per mole. So this is the answer you should be finding using all these values. I want you guys to work this on your own, though, and see if you can get to the correct answer.